In the last period, we have derived a very important and powerful equation, that is pressure of an ideal gas. The pressure of an ideal gas is equal to 1 by 3 n number density of molecules multiplied by mass of a molecule to the average of velocity square. So this is the pressure exerted by gas or pressure of an ideal gas. If we multiply this equation, let it be equation 1 multiplied equation 1 by volume of gas V, then we have PV is equal to 1 by 3 NV m V bar square. So here in place of small n we can write capital N, and if we multiply half and 2 to this equation, we have PV is equal to 2 by 3 capital N. This is the number of molecules. Here it is the number of molecules per unit volume. It is capital N is the number of molecules in a given amount of gas multiplied by half m V bar square. So don't worry why we have 2 here, because we are multiplying this equation by 2 and dividing by 2. So as a result we will get this equation. So there is no change in the expression of product of pressure and volume. So here N is the number of molecules in the sample or given gas. So this is the quantity of average translational kinetic energy. This is the expression of average translational kinetic energy of the molecule in the gas, because here we are considering till now only the straight line motion of the molecules. Since the internal energy of an ideal gas is only due to the motion of the molecule, that is kinetic, therefore expression of energy is the product of number of molecules given in the sample to the half of mass of the molecule multiplied by average of velocity squared. So this is the expression of energy. So this equation become, let it be equation number 2. This equation can be written as PV is equal to 2 by 3 capital E energy. Okay, so here this energy can be written by 3 by 2 P by V, PV, okay, product of pressure and volume. And we already have equation of state or gas equation, so we can write here energy in the ideal gas sample is equal to 3 by 2 Boltzmann constant multiplied by number of molecules multiplied by absolute temperature. So if we divide both sides of the equation by number of molecules in each side, it will be half kBT, 3 by 2 kBT. So this is what energy per molecule. Okay, the E by N is the energy per molecule, and one molecule have 3 by 2 kBT T. T is the absolute temperature of the gas. So the average kinetic energy of a molecule, average kinetic energy of a molecule is proportional to the, it is directly proportional because 3 by 2 is constant, kV is constant. So directly proportional to the absolute temperature of the gas. So we can write E by N, average kinetic energy of a molecule, is directly proportional to the temperature, absolute temperature of the gas. So this is an important equation because this equation gives the relation between the macroscopic quantity and the microscopic quantity or molecular quantity, because capital letter T is the absolute temperature, which is a macroscopic quantity, and E by N, that is energy per molecule or energy of a molecule, is a microscopic, or we can say at molecular level. So this relation bridges between the quantity at molecular level to the macroscopic level. So this equation is called kinetic theory, or kinetic interpretation of temperature. So kinetic interpretation of temperature. So from this equation, we see that the mean kinetic energy of a molecule is directly proportional to the absolute temperature of a gas. When temperature of a gas increases, the mean or average kinetic energy of a molecule increases. On the other hand, when the temperature decreases, or when we reduce heat or withdraw heat from the system or from gas, the mean or average energy of the molecule decreases. Thus, the temperature of a gas is a measure of the average translational kinetic energy per molecule of the gas. This is known as the kinetic interpretation of temperature. Though we start with the pressure expression and we have volume part also, but for a reactive ideal gas, the energy of the molecule is independent of pressure and volume, or yes, pressure and volume. But for a mixture of non-reactive ideal gas, um, total pressure gets contribution from each molecule, and we express the pressure as 1 by 3 N1 M1 V1 bar square plus N2 M2 V2 bar square, like that for numerous molecules. So in equilibrium, what happens? The average kinetic energy of molecule of gas will be equal. So in equilibrium, the kinetic energy, average kinetic energy of the molecule for different gas will be equal. That is half m1 v1 bar square is equal to half m2 v2 bar square m3 v3 bar square is equal to, like that, 3 by 2 kBT. What we have obtained here, okay, this equation. So pressure P is equal to N1 plus N2 plus N3, like that, till the number of electrons, or molecules, multiplied by Boltzmann's constant and absolute temperature. So this is known as Dalton's law of partial pressure. We already seen that from Boyle's law and Charles' law, and here we get expression for Dalton's law of partial pressure. That means the pressure exerted by each molecule of a gas. So this is known as law of partial pressure. So using equation number 4, this if we divide by half m on both sides of the equation, then we have V bar square is equal to 3 Boltzmann constant multiplied by absolute temperature divided by mass of the molecule. So it is the root mean square speed. If we take a square root of this value, we have what? It is 3 multiplied by Boltzmann constant absolute temperature divided by m. This is called the root mean square speed of the particle. Root mean square speed of the particle denoted by VRMS. So VRMS is equal to under root 3 Boltzmann constant absolute temperature divided by m. So this gives us, on putting the value, we get nearly, it is 516 meter per second square, which is nearly equal to the so VRMS or root mean square speed is equal to 516 meter per second. So this is in the order of the speed of sound, and from equation of kinetic interpretation of temperature 3 by 2 Boltzmann constant multiplied by absolute temperature, we come to know that at same temperature lighter molecules have greater RMS speed. Okay, so